So in part 3 of this video series, we're asked to continue along deriving expressions that will allow us to ultimately solve for the temperature of the adiabatic flame here for this combustion reaction. Now in this video, I'm going to continue talking about what I briefly talked about in part 2 of this video series, is that we have to take into account that we have a change in the heat capacity here. Since we have our air here and our natural gas, before they combust in this reaction, they're at an ideal gas state. So let's say 298 kelvins here. And then after they're combusted, in a combustion reaction, we may be heating these substances up to something like 2,500 kelvins or 3,000 kelvins or something like that. So when we have a major fluctuation in temperature like that, we have to take into account that the heat capacity now depends on that temperature change, and such a large change. So what we can say here, we have our heat capacity here. So I'll write that as Cp, which is commonly referred to a variable name for heat capacity. And we have heat capacity is equal to the partial derivative of enthalpy with respect to temperature. And this is at constant pressure. So this here is equal to dH. So this here is just basically the definition of heat capacity. And since we're ignoring effects of pressure here, we'll have our dT here at the end. Okay? So like I said, since we have a major fluctuation in temperature here, we'll have to account for a change in Cp here. Now, if we didn't have that major fluctuation, so let's say maybe we're just going up 10 kelvins or down 10 kelvins or whatever the case may be, this Cp here would just simply be a constant. But since, like I said, we have a major fluctuation in temperature, we'll actually have to integrate our Cp here to find the change in how it depends on temperature. So if we further derive here, we'll see that we have our delta H here, which will be our change in enthalpy, will be the integral of our dH here. So we'll have dH. And this will be evaluated at our first temperature here, so before the combustion reactions, and then our final temperature here. So we'll have, let's say, temperature 1 and temperature 2, okay? And then we'll write this as H1 and H2 since it's the change in enthalpy here. And this here, we can ultimately say that we have the integral of Cp from T1 to T2. So in order to find how this heat capacity here depends on temperature, there is an equation that we will be using, and it's commonly known as equation 107. And I'll go into that in a minute here, but essentially what this equation will do is it shows the dependency of the heat capacity here, its dependency on temperature. And what we can do is we can go ahead and integrate that equation 107. And when we code this problem in order to solve for the temperature, we will just go ahead and plug in our integral here to account for the change in the heat capacity. So that's what we'll be doing when we actually write our calculations. So let's go ahead and look up that equation 107 and then actually integrate that. And we'll just use Wolfram alpha to integrate that, just because it'll be sort of a tougher integral to integrate by hand. So just to do it quickly for the sake of this video, we'll be using Wolfram alpha, but that's what we'll do going forward. So let's go ahead and look into what equation 107 is. Okay, so I've gone ahead and opened up Collaboratory because this is what we'll ultimately be using in order to solve this problem. And what I've done here is I've gone ahead and I've done a couple of things. First, I've imported stuff such as NumPy, numerical Python, because we will need that in order to perform our calculations for this problem. And I've also imported this CHE tools. I've cloned it in here. And essentially what this is it's some pre-written code that will allow us to get some properties of the substances that we're working with without having to manually look them up or type them in. So for instance, like if I wanted to know the enthalpy of formation for oxygen, I can just create a variable name, say that, hey, I want it for oxygen, and it will code it in that number since it's already pre-written code. So Okay, and I have it cloned in here, and this sys.path.insert, essentially what this is saying is that it's telling uh, Python here where this is located so that it can access it, so that we can have access to the code in order to in order for it to be of use in our code. So this content CHE tools is where it's located in here. So it's under files here, and it's called CHE tools. So that is just a brief synopsis of what this is here. Now what I'm going to do here is I'm going to create essentially a library of all of the compounds that we will be working with, so that we can have that the properties of those compounds easily accessible, so that we can either perform multiplications or just look at the properties if we type them in. So what I mean by this is I'm going to create a variable name. So if I just create a variable name P, that tells me P is for properties. So I'll be getting the properties, the different properties of these substances. So I have P equals CHE dot tools, or excuse me, P equals CHE dot props. And in here, I will enter in quotations the substances that we will want to get the properties from. So first, we can look at our natural gas properties. So we'll have methane, ethane, and propane. So the first one we'll have is methane. So methane. Next one is ethane. And propane. And this pre-written code is written as N-propane. So N-propane. And next we will have our the mixture of our air, which is oxygen and nitrogen. So we'll add in oxygen here, oxygen, and nitrogen. You said capitals, yep, nitrogen. And lastly, we will have the products of our combustion reaction, which if you'll remember, I said is carbon dioxide and water. So we'll have carbon dioxide, sure I spelled that right, yep, and water. Whoops, I need a parentheses there. And here we'll have water. Make sure I have all my parentheses. Yep, we look good. Okay, let's make sure this runs. So what I can do here is if I do P dot, and I can look at a bunch of different properties that I can get for these substances. So if I do P dot CP, for instance, this CP is the heat capacity here. So this CPIG is the heat capacity for an ideal gas. Now what you'll may notice here is we have all these different letters here. So CP, ideal gas, A, B, C, D, E, F, G. And you might be wondering, well, what is CP, the heat capacity of the ideal gas, B? What does that mean? Well, it doesn't necessarily mean that it's the heat capacity for the ideal gas heat capacity for substance B. This B here is a coefficient or a parameter, which we would rather say probably a parameter for the equation 107, which I discussed earlier. Now this equation 107, if you remember, I said relates the heat capacity and its dependence on temperature. So when we have a wide fluctuation in temperature, so in an example of this reaction, when we take an ideal gas, so 298 kelvins, and in a combustion reaction we may go up to 2500 kelvins or 3000 kelvins. So now our heat capacity then depends on temperature. So I've gone ahead and looked up this equation 107, and I just did a basic Google search. So I searched up ChemCAD equation 107, and this is equation 107 here. So we have y equals a plus b times c divided by t times the hyperbolic sine of c divided by t plus d, and then times,
or excuse me, this is squared, and then plus d times e divided by t divided by the hyperbolic cosine times e divided by t, and that quantity is squared as well. So a few things here. This y here obviously represents our heat capacity here. So y is our heat capacity, and this is its dependence on the temperature here. Secondly, you may ask, well, what is A, B, C, and E? Well, if you remember here in Python, if we do P dot CP, so heat capacity. So here's our A, B, and the rest of our parameters here. So we have these in our pre-written code. And the other thing that you may notice is this sine H and cosine H. I'm not going to go too in depth with this, but essentially what this is, it's the hyperbolic sine and the hyperbolic cosine. And there is a specific equation to figure this out. I think it's e to the x minus e to the negative x divided by 2, or divided by 2x, or something like that. But like I said, it's not too important. All we need to know is that we have it for this equation, and that we will need to use this equation in order to determine the heat capacity for the substances that we're working with. So this is equation 107. Now, if you remember, what we need to do is we will need to integrate this equation here. Now, if you look at this here, we have a rather difficult equation here to integrate. So this a here, we can easily integrate that. That's just a times t. And this b here, this is a constant multiplied by this term here, and this d is a constant multiplied by this term here. So what I've done here is, instead of trying to do this integral by hand, I've gone ahead and used Wolfram alpha in order to determine the integrals of both this term here, so c divided by t divided by hyperbolic sine of c divided by t squared, and as well as this term here. And we can take these integrals and just multiply them by b and d, since b and d are just constants here. So here are our integrals here. So again, c divided by t divided by the hyperbolic sine times c divided by t quantity squared. Our unit of integration here is temperature, and this is our result here. So c times the hyperbolic cotangent of c divided by t. And for our second term that we wanted to take the integral of here, we have negative e times the hyperbolic tangent of e divided by t. So essentially what we can do here, we now have all the tools that we need in order to go ahead and code out our problem here. We know that we need the enthalpy of our reactants equal to the enthalpy of what is going into our combustion reaction. And we also know that we have a dependence of the heat capacities with respect to temperature using equation 107. So that's it for part 3 of this video. In part 4 of this video, we'll actually put all this together here in Python and formulate an answer for this problem. So that's it. I will see you in part 4.